Hello, everyone. Welcome to our talk. It's great to be here in Amsterdam today. And today we'll be talking about tales from an eBPF program's murder mystery. So I call it a murder mystery because it's really catchy, but there might be a liar or two in there. We'll figure it out soon. So this is basically a story about how probably one of the most important eBPF programs in our Kubernetes clusters randomly vanished. And this is a story really about how we investigated the issue and how we got to the bottom of it. So a quick introduction about ourselves. I'm Hemanth. I work on the compute data plane team at Datadog, and I'm joined by Will, who works as a security engineer on the cloud workload security team. And if you haven't heard of Datadog, we are a cloud monitoring and observability company. And here are a few quick facts about us, but the most important one here really is we run hundreds of Kubernetes clusters with thousands of nodes in them, and all of them run Cilium, and we run on all major cloud providers. So Datadog does a lot of things, but the most important ones for this talk are a couple of things. So Datadog has a component called Datadog Agent, which runs as a daemon set in Kubernetes clusters, and Datadog Agent allows for collecting things like logs, metrics, traces, and some other telemetry to power many other products. And within the Datadog agent, we also have a product called Cloud Workload Security that allows us to detect threats in runtime using eBPF. And here's a quick outline of what we are going to talk about today. So we're first going to talk about how our users notice this issue to start with, and we'll cover some quick background on Linux traffic control and how Cilium and Datadog agent uses traffic control. And then we'll get into the core of the investigation and some of the lessons we learned during the process. So it all started with an investigation, with an incident, of course. And we manage a compute platform internally for Datadog, on top of which all the Datadog applications run. And one of our internal users started reporting connectivity issues to us. And our crime scene looked a little more complicated than this, because the issues they were reporting to us were super short-lived, and by the time we could get there and collect some evidence, the issue would totally vanish away. So our internal compute platform users were reporting connectivity issues for some pods, and the init containers seemed to be constantly crashing, and the readiness probes were failing. And there are also some unexpected network policy denials, and the whole issue was really hard to reproduce because it was constantly being resolved automatically. So the first thing we do with Cilium generally, whenever there is a connectivity issue, is we do Cilium monitor logs. And Cilium monitor logs is like looking at a real-time CCTV camera footage into your network, into your Kubernetes clusters. And you could also use Hubble for a similar use case. So when we started taking a closer look at the Cilium monitor drop logs, we noticed that we were seeing packet drops for traffic that was going from an identity called 93739 to identity number 1. And identity 1 is actually a reserved host identity, and 93739 is just one of our endpoints. And these packets look like they're SYN-ACK packets, so they're actually response packets to some other request. So because the destination is reserved host, this is actually a response packet to health checks from kubelet. So this is the reason why our health checks were failing and our pods were constantly crashing. So a quick background on how this particular flow works. So in order to allow traffic from kubelet to endpoints on the same host, every endpoint has a default policy in place, which allows packets to go from kubelet to the endpoint itself so that pods can respond for health checks. And whenever Cilium sees this ingress connection, Cilium also updates connection tracking entry so that when the response packet is ready to be sent from the endpoint to the kubelet, the response would automatically be allowed based on the connection tracking. And it looks like for this case, we were not seeing entries being updated in connection tracking. And a quick background of how Cilium in our clusters is set up. So every pod that is being created on a node gets its own virtual Ethernet pair, and every pod gets its own network namespace. So this pod's network namespace is connected to the host network namespace using this vEth pair. And by the nature of a vEth pair, every packet that is sent on one end of a vEth pair gets transmitted immediately to the other end. And Cilium also installs a few route table entries and IP rules to make sure that the packets can go in and out of the host, out of the pod. And Cilium also implements a lot of features using eBPF, and one of the most important BPF programs is a program called BPF LXC, and it has two sections. One is for ingress and one is for egress. And Cilium uses traffic control to invoke these BPF programs on those interfaces. And I'll hand it over to Will to talk more about traffic control.
Thanks, Hemanth. Yeah, so we've been saying a lot today that Cilium uses eBPF to monitor traffic. Technically speaking, there are dozens of ways to actually use eBPF to monitor traffic and potentially modify and mingle with network packets. And traffic control is one of them. The reason why we need to deep dive into it is because you need to understand basic concepts about traffic control in order to understand the murder mystery. So traffic control in general is a pretty complex subsystem of the Linux kernel that is used usually to shape the network traffic on ingress and egress. In other words, this means that given a specific interface, you can actually monitor each and every single packets that come in and out of this specific interface. It usually works with something we call a queuing discipline. So there are a lot of different queuing disciplines, but the one we care about here is the CLS-ACT one. So this one is specifically what was specifically introduced for eBPF use cases and has two main hook points, ingress and egress hook points. This means that on these hook points, you can attach eBPF programs that we call direct action TC filters. They're called direct actions because whatever the output of this program is going to decide the fate of each and every single packet. So you have three different output out of others, but the main ones are those three ones. TC act OK, which means that the packet is allowed and go through. TC act shut, which means that the packet is dropped no matter where it was going. And TC act unspec, which means that the filter doesn't really want to make any decision yet and allows the next filter to make the decision for it. Filters are identified by handles, so these are either hard-coded or numbers decided by the kernels and allocated at runtime. And you can also specify priority levels for your filters. So the priority is actually used to define the order of execution of those different filters. The lowest priority is actually going to be executed first, and at a given priority level, the program that was loaded last is the first one to be triggered. So with this background, let's see how Cilium uses and configures its own TC programs. There are three main things that you need to know about how Cilium uses TC. The first one is that the TC filters always answer either TC act OK or TC act shut. In other words, this is one way to drop packets, and this is also a way to make sure that a packet is allowed to go through to either a workload or to go out. The point here is because of this, and also because Cilium hardcodes the handle and the priority to 1. Also, side note, this is expected. Cilium, owns the network data path, so it was expected for them to use, a priority level and the handle that is high enough so that they know that they are going to be the first one to be called while the packet comes to an interface. But because of this, and because we wanted to use TC as well to implement our own network policy use case, we had to work around these parameters and figure out a way to still introduce TC filters while making sure they would be triggered. And this is why we used, so first of all, we decided to hard code again the priority 1 as well, because we wanted to use the execution ordering rule that says that the latest inserted program is going to be the first one triggered. And again, this is, the rationale behind this was that Cilium would set up the pods, set up the networking, and then we would load our own instrumentation of the different interfaces we care about. So we didn't hard code any handles because we didn't want to mandel or to choose one specific number because Cilium is only one CNI out there, and other people could be using other handles as well. And yeah, we made sure to always insert TC act and spec to be sure that Cilium would make the ultimate decision when it comes to network packets, and that would be pretty much it in theory. We also added a periodical check to make sure that our filters were still loaded. Again, we knew that other people might be using TC, so we had to make sure that once we say that we instrument a network interface, we are still here after a certain period of time. And yeah, again, that's pretty much it. On paper, everything should work fine.
Except that it wasn't, but yeah. So at this point, we've been to a lot of crime scenes, and we started to see some patterns over time. And what we realized is that the murderer, whoever that was only interested in new pods. They were not interested in pods that were already running at all. So all the reports that we were getting from our users were only talking about new pods. And as I mentioned before, these pods were completely vanishing away by the time we could get to them. So we really needed a reproducer. So at this point, because we understand that this is only happening for new pods, we created a test workload and removed the readiness checks on them and just ran it in a loop until we could hit the reproducer. And soon enough, we had one. So, and once we had that pod and the host ready to investigate, we wanted to answer the question, is Cilium actually setting up the pod network correctly, right? So we could do this in a few ways, but the Cilium version that we were using at this point in time was actually using the TC binary that's part of the Cilium agent image itself to install BPF programs through the TC subsystem. And we could use the same TC command to actually inspect if the interface, if the pod's interface has the necessary eBPF programs or not. So TC filter show dev and the pod network interface would actually tell you whether the BPF programs are installed or not. And here we could see that the egress programs were completely missing for this specific pod. And the ingress programs were totally fine, right? So we were totally confused at this point, and we wanted to understand why. So BPF has a rich ecosystem of tools available at disposal. So we decided to use BPF trace to try and understand exactly what is happening. And BPF trace comes out of the box with a lot of tools that you can use immediately, right? So we decided to use exec snoop and exit snoop. As I said before, Cilium was using the TC binary to install the BPF programs. So exec snoop will basically allow us to trace all the programs that are being started up on the host. So we ran exec snoop with a grep of TC filter, and we saw that TC filter replace commands were actually being executed for both from container and to container. This corresponds to egress and ingress sections. And we also ran exit snoop, which basically tells us the exit code of these commands, and we saw that they were all completing successfully, no issues at all. So this totally confused us again. So we reached out to the community and created an issue upstream because we were thinking that maybe the TC binary image that was baked into the Cilium agent and whatever was running on the host was different, and maybe it's some weird kernel thing. So we reached out to the community and asked for help. And within a day, we got some response from Paul and Daniel, and they seemed to think that the presence of another eBPF program called classifier ingress security on the host was what was correlated to this connectivity issues in the past, and they asked us to look into it. But we still needed proof to understand why this was happening and why exactly this is happening. So the answer to that is writing a little bit more BPF through BPF trace again, but this time we had a custom BPF trace program, and we were monitoring, we had some hook points, kprobes and trace points on both TC replace, add, destroy, and also on qdis destroy and create. And we made sure to log the PID and the probe name and also the user stack at the point where we hit this trace. And once we ran this, we started to get some really, really interesting answers. And at the beginning here, you can see that the from container and to container are being successfully installed by a PID ending with 395. 395 and 398. And there were classifier ingress security BPF programs that were being installed by a PID called 2659, and the same PID was actually destroying BPF LXC2 container and even sometimes from container, right? So what is 2659? It's Datadog agent. So was it really us all along deleting this? And here, when we looked at the stack trace, it actually told us that we were calling something called flush inactive probes. So for some reason, Datadog agent was thinking this was inactive. And at the same time, we also realized that Datadog's own CWS network policy coverage was also missing, and something's broken there too. So if only Cilium agents programs were being deleted, why was Datadog agent also being impacted? So to learn more about that, we'll talk about it. So at this point, we also wanted to understand what other netlink messages were being sent, because the TC binary does not use the netlink library directly, but the Cloud Workload Security's Datadog agent was using netlink binary to interact with the kernel. So we wanted to capture all the netlink messages that were being sent to the kernel, and we realized that there was a kernel module called nlmon that allows us to monitor all the netlink messages. So we built the kernel module, loaded it, and you could actually run TCP dump on the virtual interface, and you could get all the netlink messages. But what we realized is that the protocol that was parsing this netlink messages did not have all the information that we wanted. So we wrote a custom one that captures all these messages, and Will will talk about that.
Yeah, exactly. So we were still not really confident about what was going on, because it was clear that Datadog was deleting the program, but with all the the guardrails that we put in place and the perfect plan that we had in mind, everything should be working fine. So what's going on? Why did we end up deleting Cilium's filter? So we built another tool to get a bit more context about what exactly was going on, because the scripts that Hemanth was talking about were great to identify the faulty program, but didn't really provide the context of the different events that eventually led to the deletion. So we wrote TC Probe. It's an open source project. You can have a look on GitHub. It will output more context about the different TC operations that happen on a host. So on the right, you're going to have the output of the program, and on the left, you have some kind of a graphical representation of what's going on. So the race condition happens on startup when a new pod starts and when a new interface is set up by both Cilium and Datadog. So let's see event by event what's happening and how things unfold to a murder, basically. So first, a new interface comes online, and then Cilium creates a new CLS ActQ disk to instrument this specific interface. So far, so good. This is expected. Then Cilium moves on to installing its own TC programs. So this one specifically is on ingress, and as expected, it has prior 1, handle 1. So far, so good as well. And then CWS picks up on the new interface. So we have eBPF programs to register, to detect when new vet pair interfaces are registered. So we actually get notifications from the kernel when a new interface is ready to be instrumented. And this is how we detect the new interface and decide to add our own TC programs as well. So here you can see that we have our own classifier ingress security program, and it's using handle 2. Again, we didn't hard code any handles, so this handle is actually provided by the kernel. And the race actually occurs when we end up being faster than Cilium to instrument the interface that Cilium created. And the bad news is, because we did not hard code any handles, we end up getting handle 1, because this is the first filter on this priority level, and the kernel just grants us handle 1. The issue here is that Cilium didn't prepare for this, because they did use handle 1 as well, but hard-coded. And because one of the use cases is to atomically swap the filters, they use by default the flag to swap the filter at handle 1, which means that they atomically swapped our filter. And well, to their point, we didn't prepare for this as well, because we have a periodical check to make sure that our programs are still loaded. And by default, if they're not, then we clean up everything that the kernel gave us. In this specific case, we still believe that handle 1 is ours, and we clean up behind ourselves, which means that we end up deleting Cilium's filter. So that's pretty much the gist of the race. And the race condition is really that in some cases, we ended up being faster than Cilium to instrument interfaces, and this is what explains the fact that it was not always happening and was pretty hard to debug. All right, Hemanth, take it away.
Thank you. So how do we fix this issue today? So Cilium, as of 1.12, started supporting custom priorities for TC filters, and CWS also rolled out an update that bumped the default priority from 1 to 10, so that people using Datadog agent and Cilium, things wouldn't break for them. And if you want to use both of them together, you'd have to redeploy Cilium with a higher priority, with a priority that's greater than 10. So what did we learn from this incident, right? So we learned that TC filter ownership is very racy by design, and a growing number of products are leveraging eBPF these days. So over time, this issue is only going to get worse without explicit coordination. So every player that's using TC eBPF needs to follow the same kind of rules. So folks should always use TC act unspec or TC act short, but never TC act OK. Because if you use TC act OK, the packet would be scheduled immediately to the network card. And especially monitoring products should not do this. And do not ever hardcode the handle of one, because you would not know what other products are using. And for power users, make sure the priority and handle can be configurable so that then they can mix and match different components. And deleting CLS act QDisk is also very racy, so you cannot do it you cannot delete it in a safe way. So that's for right now, but how do we fix it the right way? So the right way to fix it is with BPF links. And the kernel had support for BPF links for a long time, but the traffic control subsystem does not have support for it. So there's some work happening upstream to add the support for the traffic control subsystem. And I think it'll be merged sometime around May 2023. And there's also a great talk by Daniel Bachman that gets into a lot more details about BPF links and traffic control BPF links and how we could use them. And do check that out. So in conclusion, this was actually not a murder. This was just an accident because there were no clear guidelines established on how different people should use them together. And this was a complex incident that actually took us several weeks to get to the bottom of. And we were really thankful for the community for all the help. And I would also like to thank some of my team members, Jared, Eric, Laurent, and Maxime, for all the help. And if you're interested in working on weird and fun networking issues like this, we're always hiring. You can reach out to either of us on email or Twitter. Thank you.